All right, so today we're going to look at time beta color segmentation to see how we've seen and how to relate that to a practical application, which is how to isolate objects in images. And that will finish this first course on color operations. And then we'll start looking into spatial operations and to look at convolution. All right, so a very typical application you have is the following. You're given a picture, and somehow you want to do some analysis on this picture. And typically, what you will have to do is to look at color and trying to say the object I'm looking at is green, so I want to isolate green. And that makes a lot of sense in many applications because indeed color is a very usually a distinctive of a particular object. Okay, so it's a good start to look at color and to start from there. So spot applications say, okay, usually the object of interest is green, and so we're trying to find all the green pixels. Okay. Even so, I said that we don't use HSV. Okay, we're going to use HSV here, and we're going to look at the histogram of the hue components. All right. So remember, kind of the point of the last part of Friday's course was to show you that, to make sure you understand that color is very much linked to histograms. Okay, so when you have to do a color analysis, usually what you need to do is you need to build your histograms and to work on your histograms. Okay, so a simple way of working here to find the green table is to look at, to work in HSV. I remember in HSV, just put that briefly back. Should be somewhere. No, it's not here. It was the first slides, previous course. But basically, the hue components corresponds to which color you're dealing with. So is it red or green? Okay, this kind of distinction you have. So that's the hue component, that's H. And you have the saturation, which tells you how are you more kind of a pastel or very faint green. So it could be green-gray, okay? Or you could be really pure green. So just means saturation means how pure your tint is, your color is. And then you have the L for luminance that tells you how bright your pixel is. Now, if you just extract the hue component of the picture and build a histogram of your hue, this is what you get on the right. So on the x-axis here, you have the hue expressed between 0 and 360 because the hue is actually an angle. Okay, so it's kind of it's a circle of color. So usually it's expressed in terms of angle, so between 0 and 360. And here on the y-axis, you have the frequency of the relative frequency of each of these hues. And this is kind of typical what you get. You had multiple peaks in your histogram, and in particular, you get a very big peak here at hue of 100, which actually corresponds to green. Okay, so there's no surprise because this table has a lot of green, so therefore when you look at the histogram of the hue, then you expect to see a big blob of, the big blob here will be represented as a peak in your histogram. And so there's two benefits of looking at the histogram. The first one is just by the visual inspection of it, you can see that peak. Okay, you can say, right, there's this big peak, so probably that's the object I'm looking at. And then as well, what you see here is the shape of the peak, and you kind of have a nice idea of putting threshold values on the hue, so you're able to do further segmentation. Okay, and this is something you will do in tomorrow's lab. Basically, using the range here of this peak, you're able to find two threshold values, so 100 and 110, and you say every single value you have for which the hue is between 100 and 110, I say it's a table. If it's not then say it's black. Okay, so here you have a binary representation of your table as extracted from your hue segmentation. That's not very clean, particularly very clean cut, and that's because actually color is very noisy, and well, the fact that you have noisy color principally comes from the noise on your sensor, so thermal noise, but as well because color is complex and light gets bounced off non-uniform surfaces, and who knows what kind of interaction the color had with a particular surface. So what looks like green from a human eye, when you look in detail at a particular pixel, it could actually be red. Okay, it's just because it's in the region is quite complex. There's a lot of different pixels of different colors, and for you, your brain, remember your cortex, visual cortex, does a lot of things. So what is obvious to you is not necessarily obvious at the pixel level. Right. So this is kind of a good start. You could further refine that process and start to look at the saturation. Okay, and the reason why you want to do this is because when you look at, say, these pixels here, you see there's a lot of false detections. So false, lots of pixels that are flagged as being green, and they're not green. And that's what I said. Basically, in this particular case, all the pixels are in the gray. They're almost gray. So they're very little saturation, and it doesn't take much for them to be either classified as red or as green or as blue. Okay, so because they're white. Okay, so white or gray means like the three RGBs are exactly the same, but it just takes for one of these pixels to be a bit higher. So you say the green component is 250, and the blue and red components are 240. So slightly lower, then they will be classified as green, right? Even so, it will look gray. So therefore, you probably want to say, well, I only want pixels that are clearly green and not just like white or gray border green, okay? And then you can do that, and you can say, right, so same story. You start from a histogram of your saturation, and they say, right, this peak probably corresponds to this is the map of the saturation channel, and you could say, right, so let's try to find same story, so find a threshold for which it's mainly the pixels on the table that are highlighted as being green, and then you can do this, and this is the result. So this is hue alone, and when you apply a secondary threshold on saturation, this is what you get. So you clean up all the little details, all the noise in the background due to colors that are gray and slightly green. Okay. Right, then you can further refine all that and get something a bit nicer. One very important point here, okay, and it's something you'll see in the lab. Mistake to do, okay, is to look at a pixel here and look at the RGB components and say green is a color which has a high green value for the channels. Okay, so you have the RGB components, and you say, if I just apply a threshold on the green component and say I want a pixel whose green component is very big, then you hope that it will work. And actually it won't, because I said, if you look at white, pixel white has values 255, 255, and 255. So the value for green is actually very high. It's 255. It's a maximum value for the green component of that pixel. All right? So if you just look at the green component alone, that doesn't tell you much about the color of that pixel. Okay? So you need to look at the three components combined together. Okay? And that's why in this case we looked at the HSV space to do a bit of that, to be able to distinguish between what is white or what is green. All right, so keep that in mind for the lab. The RGB, just looking at isolation of one particular channel, is not enough. Okay. Right. So, which brings back to color and 3D histograms. I'll show you the problem here, and it's kind of obvious. Okay. So, color. So we looked at histograms mainly in the context of one-dimensional channels. So we looked at the histogram of the intensity. we looked at the histogram of the hue. But when you look at RGB as a triplet of values, so RGB, then really what you should be thinking of is three-dimensional histograms. Okay, so arrays with tables with three rows, columns, and depths. Okay, and if you work in Photoshop or most applications, what you have is instead the histograms, say, of the green, blue, and red separately. So you have three 1D histograms, and that is not good. And I just want to show you why this is a problem. So on this picture here, you have only two of the components, so the U and the V component of YUV. And these are the coordinates of two blobs of colors. And so on the bottom left, so low values of U and V, you have green, and high values of U and V, you have purple. Right? And if you do the 1D histogram, so if you look at the histogram of U and the histogram of V, you have these two peaks that are visible, right? And it's all fine, but if you look at this different picture, which has two blobs of color, one orange and one blue, it just happens that they have exactly, this picture has exactly the same histogram of U and histogram of V, right? But the colors, obviously, between the two, vastly different, okay? So if you develop an application that solely relies on the, what we call the marginal histogram, but here the histogram on the colors independently, or the each channel, sorry, independently of the rest of the other colors, you have an ambiguity, okay? So the histograms of RGB or the histograms of U and V or even the hue component or whatever, they don't tell the whole story. And you have these ambiguous cases where one color will map to a particular component and that would be the same as other colors. All right, so when you do color analysis, just keep in mind, okay, so the takeaway from that is color is three-dimensional, okay? So if you really want to do color analysis, you should have a three-dimensional analysis of it, which means like you need to have 3D histograms and not 1D histograms. You can go a long way with just 1D histograms, okay? So we've seen that with the green snooker table. But just keep in mind, okay, colors is 3D, you have three components, they're joint, okay, they're entangled, and if you do manipulation, if you're trying to identify this, you need three something, okay? So whatever color space you have, it'll always be 3D color space. All right, does it make sense? I haven't lost you there, here. Okay, so just keep that in mind. If you want to detect color and you only have basically just one number to detect that color, it kind of should be a red flag for you. Be like, okay, I'm looking only at one aspect of that color. Okay, so with the snooker table here, we only looked at the hue component. We didn't look at the saturation. All right, which is fine. We can do a lot of things with that. Okay, for your particular application, but really there is two other components. There is in this case, there is saturation and luminance that you need to take into account. Okay? Right, so that's pretty much it. So we looked at the relationship between histograms and color. We looked, show example of histogram equalization, which was the case of finding a transformation that will maximize the spread of your colors and hence maximize the contrast of your image. And we looked at how you can look at a histogram to try to identify objects in your picture. And you've seen that with already the picture of the sky. We had be able to spot where the sky was in the histogram, and here we're able to do that kind of analysis on for isolating object in the scene. And remember, color is 3D, but you can do a lot of things with 1D, but keep in mind 3D. Right.